All right, today we get to talk about projectile motion. So, in other words, how do I hit something with a cannon and related problems? So, projectile motion is just a constant acceleration problem like we've done before, but now in addition to having constant acceleration in one direction, we're going to allow things to also move with zero acceleration in other dimensions. So, when we do the projectile motion problems, the acceleration will be equal to, in magnitude, to g, the acceleration due to gravity, in the negative y direction. So the acceleration vector is just negative g j hat. Now, the initial velocity has both an x and a y component. So the velocity at time t equals 0, we're going to call that v naught. And it's going to have an x component, which is v naught x, and a y component, which is v naught y. And then there's also an initial position for our object. And the initial position we're going to call r naught, which has an x component x naught and a y component y naught. So the free fall acceleration vector is just, as we said before, negative g in the y direction. Now, to find the velocity, I just have to integrate the acceleration. So the integral of negative g j hat is negative gt times j hat. But of course, when we do an integral, an indefinite integral to get velocity from acceleration, there's also an integration constant that shows up. And it turns out that constant is just the initial velocity, right? So if I plug in time t equals 0, I should get the initial velocity. But just because there is no acceleration in the x component doesn't mean there's no velocity in the x component. So for the x component, I'm just going to integrate 0. When I integrate 0, I get a constant. And that constant is the initial x component of velocity. And when I integrate having no acceleration in the z direction, I find that the z component of velocity is just the initial z component of velocity. Now, if I integrate, so I'm going to limit this problem just to two dimensions, x and y. So we're going to get rid of z, but no, it was just like x, right? There was no acceleration in the z direction. But for now, let's just focus on two-dimensional problems. Now, to find the position, I just integrate, right? And I integrate v naught x times I hat, and that gives me v naught x times time times I hat, but I also get an integration constant, which is the initial position, or the x component of the initial position. When I integrate the y part of the velocity, I get v naught y times t minus 1/2 gt squared, and then I also get another integration constant, which is the y component of velocity. So now I have, given that my acceleration is negative g in the y direction, I've been able to find the velocity and the position as a function of time and the initial position and the initial velocity. Now, if the acceleration wasn't constant, we get something entirely different, right? So right now, we're just assuming that there is a constant acceleration, its magnitude is g, and it's in the direction, the negative y direction. Now, when we look at how our object moves under constant acceleration, note that the x part and the y part are independent of each other. I don't have to know y to know x. I don't have to know x to know y. So oftentimes in physics, we can break out, multi-dimensional stuff into independent things going on in different dimensions. That's not always the case, but for the projectile motion, it is the case. So for projectile motion, I can break the x and the y parts out and kind of treat them separately. With that in mind, instead of writing a vector that for acceleration, velocity, and position, I can have like two separate things. I have the x component of acceleration is 0, the y component of acceleration is negative g. So for the x over here, I integrate no acceleration, and I find that my velocity is just a constant. It's just the initial velocity. There's no acceleration, so the velocity doesn't change. I integrate that again, and I find that x is just the initial position plus the initial velocity in x times time. And then if I look at the y direction, right, the acceleration in the y direction is negative g. I integrate that, and I get the initial y velocity, this y component of velocity, minus gt, right? So If the acceleration is constant, then the velocity changes linearly in time. If I integrate that again, I will get the y position of my object, which is just my integration constant y naught plus v naught y times t minus 1/2 gt squared. So going from a vector representation to thinking in terms of x components acting independent of y components, you can think about it either way. You get the same answers. You see the same physics. Now let's use these equations to solve a couple problems. So let's do this one here. A cannon fires a cannonball with a velocity of 150 meters per second in a direction which is 35 degrees above horizontal. How far will the cannonball be from the cannon when it hits the ground? So we're going to find the range of a cannon here. Assume no air friction and assume that the height of the cannon is negligible. So that means the initial position of our cannonball is effectively 0 in the y direction. Use the Snuggly Dog method. Now, if you're not familiar with the Snuggly Dog method, this is a method I created and I have my introductory physics students use, which helps them prepare to, it helps them work problems in a logical way and develop good habits solving physics problems. So I decided for this lecture I would actually model the Snuggly Dog method and go through that in this problem. So the first step, so the Snuggly Dog method, basically you take the phrase dog be snuggly and the different letters represent different parts of the process. The first step is D, which is diagram. So I need to draw a diagram of what's happening here. So over here on the left, I see this is where my cannonball is launched. It's launched with an initial velocity, which is represented by this vector here, v naught, and it's launched at an angle theta relative to the horizontal. After it's launched, it does this arc and comes and hits the ground some distance x away. The next step in Snuggly Dog is O, objective. What is my objective? My objective is to find x. And I've labeled all my variables in the diagram, so I see very clearly what it is I'm trying to find is this thing I've labeled here as x. G stands for givens. The givens in this problem are the initial velocity, the angle that the cannonball is launched at, and of course the acceleration due to gravity. BE stands for basic equations. The basic equations I'm going to use are the basic equations for projectile motion, the x and the y components of motion. Additionally, I'm going to need the definition of sine and cosine to make this work. Okay, so the next step is S, which is find a symbolic solution. So we're going to start, what we really want to find is x, so let's pull out the equation for x. It looks like this. Now, I get to choose my own coordinate system, so I'm going to decide to let the point where the cannon is, where the ball is launched, I'm going to call that the origin. So the initial x position is 0, so that goes to 0. We'll throw that out. So x is just a v naught, the initial velocity, the x component of that, v naught x, times t. So I just need to find v naught x and t. Well, v naught x is easy, right? Because I just want the x component of the initial velocity. I know theta, and so v naught x is just the x component of that, v naught cosine theta. If I draw a triangle, if I take this vector and draw a line down in y and make a triangle, I'm looking for the x component, which is the adjacent side, so that's cosine. Now I need to find t. What is the time? I need to know the time at which the cannonball hits the ground. Once I have that, I can find x. To find the time, I'm going to use the y equation. All right? And remember the y equation, that's where I have the acceleration, and it has a time in there, but it also has a time squared, because I integrated that constant acceleration twice to get y, so I ended up getting time squared. Now, once again, I get to choose my coordinate system, so I'm going to let the point at which the cannonball was launched be y equals 0, so that goes to 0. Now, when it hits the ground, it's returning back to the same altitude, which means what I want to do is I want to solve this equation for the time when y equals 0 again, when the ball returns to y equals 0. So the equation I want to solve is vy naught times t minus 1/2 gt squared equals 0. Now, if you look at this equation, both of these terms have a t in them, so I can easily factor that t out, and I get this. Now, the only way this equation can be 0 is if t is 0, or the stuff inside the parentheses is 0. And so that basically tells me that the time has to be 0, or the thing that solves that makes the stuff in the parentheses go to 0 is if I let time equal 2 v naught y over g. So why do I have two solutions? Well, the trajectory of my cannonball is a parabola. And that parabola passes through y equals 0 twice. The first time is when I'm launching the ball, 0. That's not the time that I want. I want the time when the ball comes back down, so that is that solution right there. So there I have it. I know that x is v naught t. I know that v naught x is just v cosine of theta. And I know that the time that at which the cannonball hits the ground is 2 v naught y times g. But what is v naught y? We find v naught y the same way we found v naught x, only this time we want the y component. So instead of cosine, it will be v naught sine theta. So if I plug all of these things into this equation, I find that x is equal to v naught x, which is v naught cosine theta, times t, which is 2 over g, times v naught y, and v naught y is just v naught sine theta. So there you go. Simplify that, and there's my solution. So that is how far away the cannonball is when it hits the ground. That's our symbolic solution. The next step in Snuggly Dog is n, plugging in the numbers. So I take my equation and I plug the numbers in. So v naught was 150 meters per second, theta is 35 degrees, and g is 9.81 meters per second squared. I plug that into my calculator and I find that the distance that the cannonball, how far from the cannon, the cannonball hits the ground, a distance of 2.16 kilometers from the cannon. The next step of Snuggly Dog is U, check your units. And so we look at this. Up here we have meters per second all squared. Sine and cosine are unitless, and then that's divided by meters per second squared. So meters per second all squared over meters per second squared. So that's meters squared per second squared over meters per second squared. The second squared cancels. The meter in the bottom cancels one of the meters on the top, and the units I get are meters. I was supposed to get meters for x, so the units check out. If the units didn't check out, that would be a sign that I had made a mistake. Okay, next is GG, gauge and guesstimate. So I just want to look at my answer and say, does it seem reasonable? Can a cannon really shoot that far? Well, sometimes you just don't have intuition for things when you're working a test and you just have to say, well, if it had been 1,000,000 kilometers, that probably would have been crazy. If it had been 10 centimeters, I probably wouldn't believe that. But is 2.16 kilometers reasonable? Well, I checked Google, and Google says 1.7 kilometers is the range of a typical cannon, so it's not out of the ballpark. Also, maybe the professor made up an initial velocity that isn't realistic. So 2.16 kilometers is reasonable. If it had been like 1,000,000,000 kilometers or a micron, then I would have said, oh, this is crazy. That can't be right. But there's no reason from the size of the number for me to think that I did this problem wrong at this point. Okay, the next step of Snuggly Dog is limits, trends, and known cases. So let's look at our solution right here. What properties did we expect our solution to have? Well, first of all, as the initial velocity increases, the distance the cannonball goes should also increase. And I see that, right? As v naught gets bigger, x gets bigger. And in fact, I would expect that the distance should probably go as the initial velocity squared, because the initial velocity affects both the time that the cannonball is in the air. If I have a larger initial velocity, I have a larger y component of velocity, which determines, how long the ball is in the air before it comes down again. But it also affects the velocity in x during that time. So it increases the time, and for a given amount of time, it'll go further. So it kind of makes sense that the initial velocity should show up squared in my equation, and it does. Now, as the acceleration due to gravity increases, the distance my cannonball goes should go down, and that's what we see in the equation. As g goes up, x goes down. So that's good. Zero initial velocity should give zero distance. That's a known case. And in fact, that's what we see. If I plug in 0 for v naught, I get 0 for x, right? If the angle is 0, the distance should be 0, right? If the cannon is perfectly horizontal, and the cannon's, at y equals 0, as soon as the ball comes out of the cannon, it's already hit the ground, right? And if I look at my solution, I see that if I plug theta equals 0 in, Sine theta of equals 0 is 0, x is 0, so it looks like my solution meets that expectation. So once again, I'm looking at these expectations to try and get an idea of whether I made a mistake, right? If my equation does something I didn't expect, then maybe I want to look back and see if I made a mistake. One last thing, at an angle of 90 degrees, the distance the cannonball should go is 0. Right at 90 degrees, we're shooting it straight up in the air, and it's going to be in the air for a good long time, but it's not moving in x. So when it comes back down, it's going to come back down right where it started. And cosine of 90 degrees is 0, so in fact, if theta is equal to 90 degrees, x is 0, just as I expected. The final part of Snuggly Dog is why. Yes, I did all of this work myself. So remember, when you work problems with Snuggly Dog, it's okay to ask people how to do things. It's okay to look and see what someone else did. But in the end, you need to be able to sit down and work the problem start to finish on your own, doing your own work, or else you have not learned the material. Okay, let's do one more example problem of projectile motion. A bike going at a speed of 40.2 meters per second goes off of a ramp, which is 11.5 meters off of the ground, and which is angled at 32 degrees from the horizontal. What will be the bike's downward component of velocity when it hits the ground? How hard are they going to hit the ground, basically? Well, here's my diagram. The bike starts some distance h above the ground, moving with an initial velocity v0, which makes an angle theta relative to the horizon. And then it does this trajectory and hits the ground. And what our objective is we want to find the y component of velocity when it hits the ground. All right, so our givens are, we know the initial velocity, we know its magnitude, and we know the direction, we know theta. We also know the height above the ground where the bike leaves the ramp. So the height at time t equals 0. And of course, we know that gravity, the acceleration due to gravity is 9.81 meters per second squared. So our basic equations are, well, we definitely need the v sub y equation from our projectile motion equation list, because v sub y is what we're trying to find. We want to know v sub y at the time that it hits the ground. We can find vy naught, right, because we know v naught and we know theta. We know g. How are we going to find time? Well, the equation we're going to need for that is the y equation. So when we do our symbolic solution, the first thing we need to do is we need to find the time when the bike will hit the ground. And so we take our y equation and we note that our initial y location is h. The bike leaves the ramp a distance h above the ground. So we're going to set the ground to be y equals 0. When it hits the ground, its y location is 0. So I just have to solve this equation now for time. So when I do that, I can pull everything over to the left-hand side here. That all equals 0. Notice it's like a constant times t squared plus a constant times t plus a constant, right? Negative h. That is a quadratic equation, so we can solve that with the quadratic formula. So time is just negative b plus or minus negative b squared minus 4a times c, all over 2 times a. And when we simplify that, this is what we get for the time. So now I have an equation for the time. Notice, though, there's the plus or minus, right? There's two possible solutions. Again, the trajectory will be parabolic, and the parabola intercepts the ground, intercepts y equals 0 in two different places. The bike starts up high and it hits down low, but this parabola, if I extend the parabola backwards in time, backwards in x, there's the point where it intersects the ground on the other side. And so that's not the one that we want, right? What we want is where it hits the ground over here at a later time. So if I look at the time, I have these two possible solutions. I want the one that comes later, so I'm going to choose the plus solution, the one that gives me the bigger time. So now that I have that, I will plug that into my formula for v sub y. So I get v naught y minus g times all of this stuff here. I just plug that in, right? Now notice that the g's cancel out. Once I cancel out the g's, the v naught y's cancel out, and I'm just left with negative the square root of this stuff. So there's v sub y. It's negative the square root of v naught y squared plus 2gh. And of course, v naught y is just v naught sine theta. It's the y component of the initial velocity. So I plug that in. And there's my solution. Next step is numerical. So I'm going to plug in numbers. When I do that, I plug in V naught, I plug in theta, I plug in G, I plug in H, and then I evaluate the whole thing, and I find that V sub y is negative 23.5 meters per second. So the y component of velocity when the bike hits the ground is 23.5 meters per second in the downward direction. That's pretty fast. Of course, the bike left pretty fast too. I don't know if this is really realistic. Okay, so U, right? Check the units. We have meters per second all squared, so that's meters per second squared. And we add that to meters per second squared times meters, which also gives us meters per second squared. That's good, because I can't add two things together that have different units. So everything underneath the square root is meters squared per second squared. I take the square root of that, and I get meters per second. Great. The units work. Gauge and guesstimate. Does this seem like a reasonable velocity? That's pretty fast. 23.5 meters per second. That bike's moving pretty fast. But maybe this problem isn't super realistic because we launched the bike going 40.2 meters per second, right? Now, what would I expect the velocity to be? It's negative. That's good because the bike's coming down. I would expect the y component of velocity to, at the end when it hits the ground, to be bigger than when it went off the ramp, right? Because when it comes back down to the same height it was launched from, right, there's a symmetry to our parabolic curve. So you would expect it to be going down with the same velocity it was going up initially. But to hit the ground, now we've got to go down 5.11 meters more, right? Because we were launched 5.11 meters above the ramp. So we would expect to have a downward velocity whose magnitude is a little bigger than the upward velocity we started with. Well, the initial y component of velocity is just v naught sine theta, and we can quickly calculate that, and we see, oh yeah, that is a little bit bigger than the upward velocity we started with, right? So doing that quick calculation to find the initial upward velocity is a way to look and see if our answer seems reasonable. Now, limits, known cases, trends. If I look at this, if they launch faster, they hit the ground harder. That makes sense. If they start up higher, when they hit the ground, they're going to hit it harder. That makes sense. What would happen if they had no initial velocity? Then they're just going to fall off the ramp, and that's exactly what you would find. You can quickly show that, if there's no x component, if there's no initial y component of velocity, this is how hard they're going to hit the ground. That's the velocity they'll be moving. What if sine of theta is equal to 0? What if theta is equal to 0? That's just like falling off the ramp with no velocity, because all the velocity is in the x direction. It won't affect y. What if sine of theta is 90 degrees? Oh, when I get back to my initial position, my downward velocity will just be v naught in the negative direction, but now I have to fall an additional distance. So looking at this, it all seems to make sense. If h is equal to 0, my initial y velocity then just becomes my final y velocity going in the other direction. So we can do all kinds of things to suss out whether this answer makes sense, to try and catch any mistakes we might have made. And then finally, yeah, I did this myself. That's the end of our discussion on projectile motion.